Now that we've covered the concepts, now I'm going to go into some examples. And this video, so this will be like part 4 to the video series for section 4.2/4.3. And in this video, I'm going to do 2 examples where I find approximate the area. And I'm going to use the left and right endpoints to do that, and I'll be using 4 rectangles. So, and these are from section 4.2. So I'm going to use left and right endpoints to find 2 approximations of the area of the region bounded between the graph and the x-axis, and then use 4 rectangles. So these are the 2 examples. F of x equals 2x plus 5 on the interval 0 to 2, and then f of x equals cosine x on the interval 0 to pi over 2. I went ahead and drew a picture of each graph just so we can visualize. So this is number 29. So we have a line with slope of 2 with y-intercept 5. So, and again, this is me drawing the graph. So it's not going to be picture perfect when you draw the graph. So I wouldn't rely on the graph itself to answer these questions. But I think it helps to see what you're looking at. So we're going to find the purple region is the area that we're going to try to approximate. And so we go from 0 to 2. I just went ahead and restricted it to that, and we have this green line. And so at 0, we have the y-intercept is 5, and then at 2 is the point 2, 9. All right, so that is what the graph looks like for number 29. This is the graph for number 33. So we're dealing with cosine graph, but we're only restricting the graph from 0 to pi over 2. So if you restrict the graph from 0 to pi over 2, this is what you have. And so you see it's this curve, and again, I'm going to actually use the algebra to find the answer. I'm not going to rely on the graph itself, but the graph is, again, helpful to know what you're looking at. So those are the 2 graphs. So we have a line, and then we have this curve. And we're going to approximate each one using left and right endpoints, and I'm going to be using 4 rectangles. So the solution for number 29 so I need to form my 4 rectangles. And previous video, we talked about how the rectangles are going to have equal width. So I'm going to form 4 rectangles of equal width. Which means I need to form 4 subintervals. And our interval that we have is 0 to 2. So if we cut that into 4 pieces, you would have the following 4 subintervals: 0 to 1/2, 1/2 to 1, 1 to 3/2, and 3/2 to 2. So these all have the width of being 1/2, or the length of these intervals are all 1/2. And in the previous videos, I talked about that delta x represents the equal width, and that's equivalent to doing b minus a divided by n. In this case, a is 0, b is 2, and we want 4 rectangles or 4 subintervals. That's going to be 2 minus 0 divided by 4. So this will be my width, or the length of each subinterval. And so you basically form the first one 0 to a half. You just add 1/2 to 0, and then keep going. Add a half to 1/2, you get 1, and then add a half to 1, you get 3/2, and then add 1/2 to 3/2, you get 2. All right, that's how I generate the 4 subintervals. And I'll first do the left endpoints. All right, so what I'm going to do is I generate the heights of the rectangles by plugging in the left endpoints of the subintervals. So generate the height by finding f of ci, where ci in this case is going to be the left endpoint. All right, so my options are, for the first interval, I have 0 to 1/2, so the left endpoint is 0. So I'm going to have C1 equaling 0, and I plug that into my function. And the function is 2x plus 5. Okay, so that's going to be, and we know that's going to give you 5, right? Because that's what the y-intercept is. So 2 times 0 plus 5 gives me 5. So that's the height for the first rectangle. And I'll say that's h1 for height. So the next left endpoint, so we've dealt with 0. Now the next one's 1/2. It's 2 times a half plus 5. So that gives me 6. And then the next one's 1, plugging in 1, right, because that's the next left endpoint. And you know that's going to be 2 plus 5, which is 7. And then the last one is 3/2. Right, so that's going to give me 8, right? So they're all going up by 1s as far as going from each particular value to the next. All right, that's the height of the fourth rectangle. All right, so now I know base times height is the area of a rectangle. I have 4 of them. So I can get the overall area approximation. So the area will equal the area of the first rectangle plus the area of the second, and then the third, plus the fourth. And we know area of a rectangle is base times height. So this would be the base times h1, base times h2. We know they all have the same base, right? Because it's all equal width of a half. So plugging in a half, we get, we can factor out the 1/2 that's in common, and then just sum up the heights of the rectangles. All right, so that's going to be 1/2 times, and then I just plug in the values 5 plus 6 plus 7 plus 8. All right, so that's going to give 13. So the approximation using the left endpoints is 13. All right, so then the right endpoints, I'll do that different color. All right, so our first right endpoint is C1 is going to be a half, C2 is going to be 1, C3 is 3/2, and then C4 is going to be 2. Now notice when you plug in 1/2, we already know what that's going to be. When you plug in 1, we already know what that's going to be. And 3/2, we already know what that's going to be because we found them earlier when we were doing the left endpoints, right? Because the 1/2 value, that's our first right endpoint, is the same as the second left endpoint. So knowing that, we know we're going to be adding 6 plus 7 plus 8. Those correspond to 1/2, 1, and 3/2. And then in addition, then you do 2. All right, so I'll go ahead and write it out, but that was a pattern that we can recognize. So the first right endpoint is a half. And we found that right here, you get 6. And then the next right endpoint is 1, which we already found, which was 7, right? Because that's the third left endpoint. It's the same as the second right endpoint. And then 3/2, we got that to be 8. So the one that we need to actually plug in now for the fourth right endpoint is 2, which we know is going to give you 9 based on our pattern of it increasing by 1. Because if you plug it into 2x plus 5, that's 2 times 2 plus 5. All right, so I hope that makes sense. I skipped showing the work for the first 3 because we've already found those earlier. They matched up with the particular left endpoints. So the last 3 left endpoints matched up to the first 3 right endpoints. And then the one that's in addition is plugging in 2. So now the area so base times height plus base times height, we know they all have the same base, so we can factor out that common base of a half, like we did earlier. So we know it's 1/2, and then adding up the heights. So it's just 1/2, and then we're adding up 6 plus 7 plus 8 plus 9. Okay, and that comes out to be 15. All right, so the approximate area using the right endpoints is 15. So we found bounds for the overall area under the curve, and that the bounds are, we have 13's less than the real area, and then less than 15. So this 13 came from the left endpoints, and then the 15 came from using the right endpoints. All right, and that's what we're supposed to do for that one. I will show visually. I'm going to pause the video for a second and copy this graph over again. All right, so I drew the cases where we had the left endpoints and right endpoints. So the one on the left is the left endpoints, and the one on the right is the right endpoints. And so you'll see that the left endpoints undershoots the actual area. And then the right endpoints overshoot. And this is because our graph is an increasing line. So this is because our graph is increasing. All right, that's what happens when you use the left endpoints and right endpoints when you're only using just a small value of rectangles. If the graph is decreasing, it's going to be the opposite. So the left endpoints would overshoot and the right endpoints will undershoot if it's decreasing graph. All right, so I thought I would mention that pattern, that if the graph is increasing, left endpoints are going to give you an approximate area that's less than the real area. And if you use the right endpoints, it's going to give you an area that's going to be approximately somewhat more than the real area. All right, and I didn't rely on the graphs themselves to find the approximations. I just plugged in the endpoints of each interval into the function, and that gives me the heights of the rectangles, and then I use the fact that the base is the same, it's 1/2, it's the equal width. All right, so that's it for that one. Now for the next one, number 33. Notice our interval is 0 to pi over 2, and we want to do 4 rectangles again. So we need 4 subintervals, and they're going to be 4 subintervals of the same length. So 4 rectangles. You need 4 subintervals. It's going to be equal width or equal length. And that's delta x is equal to b minus a over n. Our b is pi over 2, a is 0, so it's going to be pi over 2 minus 0 divided by 4. So that's pi over 2 divided by 4, which is going to be pi over 8. All right, so the width is pi over 8. And that's the length of each subinterval. So I generate the 4 subintervals. So I start with 0 and add pi over 8. All right, that's the first one. The next one, I start with pi over 8 and add pi over 8. Well, that's going to give me 2 pi over 8. Well, 2 pi over 8 is pi over 4. Next one, I start with pi over 4 and add pi over 8. So we know pi over 4 is 2 pi over 8, and if I add pi over 8 to that, that's 3 pi over 8. And then add pi over 8 to 3 pi over 8, and that should give us pi over 2, which it does because that's 4 pi over 8. All right, that's the 4 subintervals, and I just kept adding pi over 8 to generate them. And now I'm going to find the approximate areas. Now keep in mind our function is cosine x. So I'll again use the same colors as last time. I'll do green. And again, we're just plugging these endpoints into the function. The first one is 0, and then cosine of 0 is 1. Right, so that's the first height. And then the next endpoint is pi over 8. And then the next one's pi over 4, and then 3 pi over 8. So there's no value on the unit circle for pi over 8. And so I'm just going to leave it as is. And then at the end, that's when I plug everything in the calculator. So I'm going to say that's H2 is cosine of pi over 8. Now C3 is pi over 4. And there is pi over 4 in the unit circle. So pi over 4 for cosine is square root of 2 over 2. All right, and the last one is going to be 3 pi over 8. And that's just going to be cosine of 3 pi over 8. And there's no 3 pi over 8 on the unit circle, so I would just leave it like this. So that's H4. Now I find the area, and we know the area is going to be A1 plus A2 plus A3 plus A4. That's base times height. And they all have the same base, so I'm just writing as B for each one of them. The base are the same, it's the same as width, right? So it's pi over 8 is the width. So I factor that out. And then I'm adding H1 and so forth. So H1 is 1, H2 is cosine of pi over 8. And then H3 is square root of 2 over 2. And then H4 is cosine of 3 pi over 8. All right, and that's what I would put in the calculator, pi over 8, and then I put the whole thing that you see in parentheses, 1 plus cosine pi over 8, and then plus square root of 2 over 2, then plus cosine of 3 pi over 8. And then that's where I'll round. And I'll just use 4 decimal places. So when you do this, you should get 1.1835. All right, that's the area using the left endpoints. Now the right endpoints. Well, what do we know for our pattern here is that the first right endpoint is pi over 8. That is the same as the second left endpoint. And then, so we know what that's going to be. And then pi over 4, that's the same as the third left endpoint. And then 3 pi over 8 is the same as the fourth left endpoint. So pi over 2 is the one that's different. So we already know the first 3 right endpoints, since they are the last 3 left endpoints. So we know pi over 8, that was C2 for the left endpoint, and that's just cosine of pi over 8. And then let's see, so the next one after that is pi over 4. And we know that gave us square root of 2 over 2. And then C3 for our right endpoint is the same as C4 for the left endpoint, so 3 pi over 8. And we just left it as cosine 3 pi over 8. All right, that's the third height. And now C4 is what's different. Now we have pi over 2. And that's cosine of pi over 2. Well, cosine of pi over 2 is 0. All right, so I have all 4 heights. Now I'm going to find the area. So we know it's base times height. They all have the same base. The base was the same as before. It's pi over 8, right? That's our equal width, the length of each subinterval. So I'm going to go ahead and just write it as pi over 8. And then in brackets, I add the height. All right, so that's pi over 8, and then times. And then I just write down what is h1 and so forth. So that's cosine pi over 8 plus square root of 2 over 2 plus cosine of 3 pi over 8. And h4 is 0, so plus 0. And then I put all that in the calculator, and you get this to be 0.7908. All right, and that's the area using the right endpoints. So based on what we have 2 bounds, and our bounds are, we have 0.7908, that's the lower bound. That's going to be less than whatever the real area is. And then less than the upper bound, the bigger value was 1.1835. In this example, the 0.7908, the lower bound, came from using the right endpoints. And then the upper bound came from using the left. And notice our graph, we have a decreasing graph. All right, so it's the opposite in this case. So it's decreasing graph. That's why it's flipped. All right, and that's pretty much it for these two examples. The next video, and I didn't use the formal definitions for Riemann sum. I just went off of just adding base times height and plugging in the values in to get the heights. So the next video, I'm going to cover examples of using the Riemann sum. So finding this. All right, so that's it for this video.